robotic sounding. Welcome back, everybody. We are going to hit section 9.3, and this is on infinite series. So an infinite series, just slap DEF down definition. An infinite series is an expression written as, it's a summation thing, k equals 1 to infinity of u sub k. So it's like u1 plus u2 plus u3 plus u4 on to infinity. And u1, u2, u3, these are terms in the series. And the subscript denotes which term? But we're going to backpedal this because oftentimes when we do infinity, we do a limit. So we're going to look at something called a partial sum, which is going to end up being a finite series. A finite series has an end. K equals 1 to n of uk. So it'll be u1 plus u2 plus u3 plus un minus 1 plus un. And it stops. We call this S sub n. And it is, in words, is the nth partial sum. This dragon drink at Starbucks is really fucking good. Never tried it before this week. So let's look at a few of them, just in general. So S sub 1 is doing k equals 1 to 1 of u sub k, and that's just u1. S sub 2, k equals 1 to 2 of u sub k, so u1 plus u2. S sub 3, guess what we're doing on this one? K equals 1 to 3, u sub k, u1 plus u2 plus u3. And we'll go dot, 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 down to S sub n, k equals 1 to n, as we had above. And you'll notice we have S1, S2, S3, Sn. This is a sequence. We've created a sequence of partial sums and so if we wanted the infinite sequence, we could call this, using the curly brace notation, S sub n from n equals 1 to infinity. This entire chapter has a lot of algebraic manipulation in it, a lot. And some clever thinking that once you've seen it, you're like, okay, that can do that. But like making that jump isn't necessarily intuitive. Okay. So we're going to say the sum of a series. At least you're still writing it. Definition. The sum of a series. The infinite series k equals 1 to infinity of u sub k converges to the sum s Have you guys ever seen that before? IFF? So that means if and only if, which means this is like a two-way street. One means the other. If A, then B, and then if B, then A. That's what IFF is. If the sequence S sub n, n equals 1 to infinity, partial sums, sequence of partial sums, converges to S. Now, if you think about this and think about what a series is, wrapping your head around a series takes a little bit of time. A sequence of numbers is things, but like the series, S sub 1 is adding up the first number, S sub 2 is adding up the first two numbers, S sub n is adding up the first S or n numbers. If I add S 1000, it's adding up the first 1000 numbers. If I go to infinity and like they all start being the same value, we're going to the same value. Yeah, it's got to be the sum. That's all this is saying. And sometimes figuring out this is easier than figuring out this. So one way of doing this is we'll take the limit. I'm going to say as k goes, well, let's do limit at, let's start out with S sub n, what it is. S sub n is k equals 1 to n of u sub k. And we are going to slap some limits on this. Limit as n goes to infinity of S sub n equals limit as n goes to infinity of this summation, which makes it an infinite series. more summation k equals 1 to infinity w sub k. So we can find out what it converges to by taking the line. Take the limit. That's what we're going to do. Work with partial sums and take the limit. So what do we have under our tool belt so far? The only things we have that we've learned to do is, we have the definition of the sum of the series. Which isn't all that helpful. And we also know how to do the limit as n goes to infinity of a sub n from what we were doing before. This could be done, we can see, using the monotonic convergence principle from 9.2. We got some things under our belt that we can try. So we're going to take a look at an example. Let's explore the sum is k equals 1 to infinity of 1 over 2 to the k power. And we're going to look at the sequence of partial sums. Because sometimes writing out a few of them really gets you a feel for what's going on. And you can almost guess what it's going to be even before you apply some of the rules that we're going to learn. So S sub 1 only has one term. It's 1 over 2 to the first power, which is 1/2. S sub 2, 1 over 2 to the first power plus 1 over 2 to the second power. 1/2 plus 1/4 is 3/4. S sub 3, 1 over 2 to the first power plus 1 over 2 squared plus 1 over 2 cubed. The first two were 3/4. We have 3/4 plus 1/8. Get a common denominator, 6 over 8 plus 1 over 8 is 7 over 8. Go back to red. S sub 4 here. You know what? Let's get smart. Let's write it as S sub 3 plus the new term. Oh, save yourself some writing. This is 7/8 plus 2 to the fourth power is 16. Multiply that by 2 over 2. And we're going to get 14 plus 1, 15/16. S sub 5 is S sub 4 plus 1/2 to the 5th power. So 15/16 plus 1/32. If I look at this over here, I multiply this by 2/2. I'm getting 2 times 15 is 30 plus 1, 31/32. So if I do S sub n, we're looking at this series here. Well, it's going to equal 1/2, 3/4, 7/8, 15/16, 31/32. Can you guys see where it might be going to? What value do you think it's going to end up at? It's going to get really like the top is just a little bit below the bottom. This is approaching 1. So that's what we think it's going to do. We can see it's increasing. It does have an upper limit. It's increasing. Each of these values is increasing. So it's monotonic. And it looks like the upper bound is 1. Can we show that though? Do you guys see a relationship on each fraction? How would you describe that relationship? So the numerator is the bottom minus 1. So S sub n in general is going to be the numerator, or is the bottom minus 1 over the bottom. What's the bottom though for S sub n? It's 2 to the n, which means the numerator is 2 to the n minus 1. Oh, minus 1 like that. So if we take the limit of as n goes to infinity of S sub n, we're taking the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Now, if you plug it in, this is infinity over infinity. We don't want to go down the whole L'Hopital route, because just the top and bottom quickly start looking the same. Actually, let's do that. This is infinity over infinity. This is L'Hopital event worthy. Does it help any though? You should always check. What's the derivative of the top? So if we do e to the x, it's normal, but here it looks like we have a different base though. This is like 2 to the x. If you remember derivatives, you could do like logarithmic differentiation. I want to say this goes to ln of 2 times 2 to the n minus 1 over ln of 2 to the n minus 1. I'm pretty sure that's the derivative of b to the n. What?
I thought it was ln of 2 divided by 2. Or
I'm looking it up real quick. You don't take the derivative of b to the x very often.
no.
And rather than re-deriving it right now, Nope, it's b to the x ln of b. So this didn't even go down. It doesn't go down by a power. I'm trying to combine the fucking power rule in my head. But now some shit cancels, right? In fact, it all cancels, and we're left with one. Let's face it, who's gonna remember the fucking derivative of b to the x? Your teacher didn't. I'm betting no one got it right. Got close, but didn't get it right. So let's look at doing that a different way. Let's break that up. That is the limit as n goes to the infinity of 2 to the n over 2 to the n minus the net limit as n goes to infinity of 1 over 2 to the n. Limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over 2 to the n. This is 1 minus 1 over infinity, which is 0 there, and this is 1. And then we didn't need to worry about L'Hopital. All we had to do is separate the fraction. I'm gonna show you another way, and you're gonna be like, what the fuck, why? But we're gonna do something similar later on to actually find the answer for something else. So I'm gonna show you another way to do this. So S sub n was, we had 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot dot dot. I'm gonna write this as 1 over 2 to the first plus 1 over 2 to the second. And this is going all the way up to 1 over 2 to the n on both. Now we're going to multiply by 2. 2 s of n we're going to distribute to everything. 2 over 2 is going to be 1. This is going to be 1 over 2 to the first power. And the 2 is going to cancel out one of the 2's on the bottom. You're going to love this. You'll be like, what the fuck? All right, so like this is almost S sub n as it is. It's almost what we started with. So what I'm going to do is I'm going to add in a 1 over 2 to the n, and I'm going to subtract 1 over 2 to the n. That won't change the value. But it is going to allow me to group this. Don't ask me who came up with this bullshit. Like I said, there's a lot of clever gimmicks in this chapter that, like, once you see them, you're like, okay, I don't know that I ever would have even thought of doing some shit like this. But if I subtract S of n from both sides, I get S of n equals 1 minus 2 to the n. 1 minus 1 over 2 to the n. That's if you didn't recognize the pattern earlier. And now hit it with the limit and you're back to where we were. So we've shown a couple ways that the sum of k equals 1 to infinity of 1 over 2 to the k actually converges to 1. I don't know why there was something crunchy in my drink, but I just crunched.
What's the dragon fruit things?
It was, yeah, it tasted like dragon fruit, but like it didn't have like that a fruit thing.
But just that they're drying.
Oh, so it hadn't fully hydrated yet. That makes sense.
My question, how does the adding with the
This doesn't change it.
yeah, but how does that adds to the bottom?
Does this look like this before I multiply by 2?
Oh, no, it's
Now I see it. Right, it's some shit that you'd be like, nope, I would never have thought of that. I'm no fucking Isaac Newton. I strongly suspect I'm not gonna meet an Isaac Newton or anybody that fucking smart in my life, but I've met a lot of smart fucking people. But to come up with some of this shit from scratch. I don't know that Isaac Newton did this, but with calculus, so like. Part of it at least.
And there was that kid, it was a couple years back now, but it was that guy who figured out how to it was add up all of it digits between like 1 and 100 real quick or whatever.
Oh yeah,
It's amazing.
it's a famous person too.
Yeah, he went on to do a lot.
If you take computer science 1 with John Redden, he will tell you who it is. I'm pretty sure he will. He's got pictures in his house. He put them up on Zoom. I've seen them. They might be in his office now. It's famous computer science people and famous mathematicians. Like we're talking like the good old black and white picture kind of thing. I think he should have been a math historian, to be honest. He loves that shit. All right, let's look at a new type of thing called telescoping series. And we're gonna like lead our way into it. Does the summation of k equals 2 to infinity of the natural log of 1 minus 1 over k plus 1 converge? If so, to what sum? So what we're gonna do is we're just gonna do a little bit of algebra, do a little bit of manipulation here. This is the natural log of, I'm gonna change that 1 to get a common denominator with the other fraction. And now we'll combine those two fractions. You can see that's natural log. I don't know why I'm feeling like I gotta write it over here. K over k plus 1. So natural logs can be pulled apart. When it's done as division, it turns into subtraction of the denominator. So let's look at a partial sum S of n. So k equals 2 to n. If I do the 2, this will be ln of 2 minus ln of 3. I'm going to write what n I'm on above it. And then we're adding n equals 3. N equals 3 will be natural log of 3 minus natural log of 4. And then we're going to add n equals 4. Plus natural log of 4 minus natural log of 5. Plus, maybe I shouldn't be doing n. I should be writing that as k. We're on k equals 2, k equals 3, k equals 4. If we look at the k equals n minus 1, we're adding natural log of n minus 1 minus natural log of n. And then I get up to k equals n. And I have the natural log of n minus the natural log of n plus 1. Then pause and let you get this all written down before we point out where the series, why this is called telescoping series. All right, notice we have a minus ln of 3 and a plus ln of 3. A minus ln of 4 plus an ln of 4. And that pattern is going to keep continuing. The ln of n minus 1 here is going to go down with the n minus 2 one. The negative ln of n plus ln of n cancels there. And this condenses down into ln, let's see. I'm doing this condenses down into ln of 2 minus ln of n plus 1. So this isn't like one of those nice telescopes that you look through and they're fucking hella expensive. This is one of those, like, you could put them on your fucking pocket and you whip them out and you fucking open it up like pirates you see on fucking pirate ships, and they fucking pull it out and they look through one thing and it extends. They also collapse. So it's like a collapsing telescope. And that's what this is doing. Each level is collapsing with part of the level before it until all the middle shit is done and you only have the start and the end. Or the eyepiece and the fucking lens. And that's S of n. So if we want to see if it converges, what do we have to do? we have to take the limit as n goes to infinity of this. This shoots to infinity. So this is divergent. So since the partial sums diverge. Means that the very thing we started with, k equals 2 to infinity, ln of 1 minus 1 over k plus 1, also diverges. You guys ready for another example? Nope, some people still writing, slow your shit, Jones. All right, let's take a look at, oh, I know this will be your favorite. What's your favorite number, Dalton? What? You don't have a favorite fucking number? Michael, what? What's your least favorite number? Good, let's go use that, because I know this is probably your least favorite here. Let's do 3 over k plus 2 times k plus 3. That's gonna be our summation. We'll do k equals 1 to infinity of that. Why is that gonna be your least favorite? What do we need to do on this one? Partial fractions, that's right. This actually isn't too bad. If we clear fractions, what do we get?
A times the k plus 3 plus b plus c.
She's like, I like this partial fraction decomposition problem.
Starting with Tracy.
Oh, were you?
Yeah.
She does a problem similar to this. She did k plus 1 and k plus 2. I'm like, let's change it. In case you've taken the class with her or studied with her before. Some of them are the same, but just that's because they're in the textbook and they're simple ones to do and get. So what will we do here? Dat. That's the hard way. What's the short way? There we go. Work smarter, not harder. Working out the long way, well, it works, but that's what got most of you in trouble on the test. If I stick in -3, this is a times 0 plus b times 5. Which means b equals 3/5.
Isn't it -1?
-1. How about -1? And b equals -3. There we go. How about that? Where the fuck did I get 5? I added +3. And we're doing that one. Maybe I should write it in rather than just fucking jumping the gun here. Clearly, I need to because I'm fucking shit up. So A equals 3. So this can be rewritten as the sum of 3 over k plus 2 minus 3 over k plus 3. Really, plus negative. So we'll do S sub n equals k equals 1 to n of this ruckus. And let's write out a few terms. I've got 3 over 3 minus 3 over 4. That's k equals 1. If I do k equals 2, I've got 3 over 4 minus 3 over 5. Maybe I should do one more. K equals 3. Make sure everyone sees the telescoping effect. And deliberately not reducing fractions here. K equals n minus 1. N minus 1 plus 2 would be n plus 1 minus 3 over n plus 2 plus the k equals n term, 3 over n plus 2 minus 3 over n plus 3. And I think this blue pen is dying. Let's move this out of sight and grab a fresh blue pen. So these are canceling in pairs. And S sub n reduces to 3 over 3, which is 1, minus 3 over n plus 3. And if we do the limit here, the bottom goes to infinity, which means the whole thing goes to 0 there, and we're just left with the 1. So telescoping series in general, you have some coefficient, let's call it c, times f of k minus c times f of k plus 1. So this would be like this one here, f of x. C f of x was 3 times 1 over x plus 2. If I plug in k, I get k plus 2. If I plug in k plus 1, I get k plus 3 on bottom. But they're gonna have the same coefficient. And one term is subtracting the next term. Term n is subtracting or minus term n plus 1. And they have to have the same coefficient. Otherwise, it won't cancel. That's telescoping series in general. Maybe I should go back and finish this one. Since the partial limit or the partial sum converged to 1, then what we started with, k equals 1 to infinity, 3 over k plus 2 times k plus 3 also converges to 1. And let's take a 10-minute break before we start the next part, geometric series.
On favorite number, that's not real.
E to the I theta.
Okay, let me rephrase it. No,
No,
It's-
that's not up your cup of tea.
no, so
Define not real.
you don't use it in math. It's made up, but I mean, I guess all.
What number do you not use in math?
11d7,
Like,
so it's 11d7,
like 11 over 7?
but you see, you make the 11s e, so it's 11d7. It's not a real number, but like I
Wait, so I got 11, and then what do I put?
then you, so you.
I'm wearing glasses and you're writing from fucking 10 feet away.
Yeah, I'll put a line underneath it. So then you make both 11s a D,
Got it?
and then you write a 7 underneath it, so it's 11d7.
That's not a real number.
Yeah, exactly, I told you it's not a real. But then I realized that, you know, real numbers are a class of numbers.
This is just 1/7 of DD. Or 1/7 of D squared. If DD is not a variable. Yeah,
Yeah.
I'm just changing shit around on you, honestly.
Yeah,
What I heard. So this is Michael's nonsense.
yeah, no, that's just a joke from a long time ago.
Michael's nonsense was 11. I heard 11d7. Now, to me,
Yeah.
this is rolling 11 7-sided dice.
You know, I never thought of it like that.
Because 3d6
So,
is if you play D&D, it's how you make your stats. So this is Michael's nonsense. So when I scan this, you all know that Michael's at fault for this being in the
Yeah.
lecture notes. Nope, I want everybody in perpetuity to see this. Not only is it Michael's nonsense. Michael Kenny.
I appreciate it. It's always good to
Bullshit.
cite your sources, you know?
It's good, yeah, you know, and
You know, I
you
appreciate.
know what? Let's just go with Mikey. Cause he doesn't deserve it for Michael right now for that bullshit. Mikey's. Mikey's Kenny's, that just sounds funny. Mikey Kenny, you're welcome.
Appreciate it.
If you wrote that down, make sure that's in your notes, Mikey Kenny.
Can't remember how long ago I first heard that joke. It must.
I think we're using the word joke very loosely here,
Yeah,
because I don't know that anyone laughed.
oh, we all laugh.
Who's we? You've got a
No, no.
mouse in your pocket?
No, this
Split
was,
personality?
no, this was,
Your 6-year-old friends that you did this with?
No,
Now everybody's laughing. See, now it's a joke. But now it's just me making fun of you.
exactly.
That's not as much fun. That's me being mean to a student. I shouldn't do that.
I'm trying to remember how long ago.
You can all tell you're like, go to the Mesa Center, Mr. Jones is abusing Michael. Maybe not say like heckling him.
There you go.
Abusing might sound like slapping him around or some shit.
No, I
Or
would-
calling him names. Other than Mikey.
Yeah.
I did call him Mikey.
That's a whole nickname.
I don't know if I made you guys sit through. I know I didn't. I like Dungeon Crawler Carl. I've worn the t-shirt a couple times. I ordered book 2 recently. And it just arrived in the mail yesterday. And that was the cover of book 2. Professor Hefe's. Personalized to me, not David Jones, but Professor Hefe. Because there's too many David Joneses and I don't want someone to steal my book and think it's theirs. There's only one Hefe. One Professor Hefe. I was very pleased with that.
No, yeah, there probably is, because I'm like, there's a lot of people, surely there must be that, I'm like, nah, that's. Pretty American English, I don't think.
Hefe?
Right,
There's nothing American about it.
where did you, I thought that was a nickname for something, right?
It is, but it's not an English word. It's boss.
Oh,
It's boss in Spanish.
Yeah,
oh, okay, I'm just uncultured.
from a Puerto Rican guy, no less. So I don't know if they speak Spanish or I thought they had Puerto Rican in Puerto Rico, but he called me Hefe and I looked at that shit up finally.
It might be very similar in Portuguese and Spanish, there's a couple that are.
Portuguese, where'd you get it? Puerto Rican?
Oh, Puerto Rico, I thought I was just thinking Portugal. No.
I get it. They both have that port sound. See, I think you're having a hard day. If you go home, when you get home, take a cloth and fold it up and put it like under some cold water. And just press it on your head and lay down for a little bit and everything will go away.
You see, that sounds great, but like, I got homework.
But you only gotta do it for a couple minutes. A hot one is soothing, but like a cold one, especially in summer, that's right. Especially if you're hot when you get home, do that and sit in front of a fan.
It's 1:05 today, it's October.
Did anyone grow up poor that didn't have air conditioning? And your parents made you stand in front of a fan with a fucking squirt bottle? You're looking at me like I'm fucking crazy, Dalton. And I'm not the only one with my hand up. That shit chills you fucking fast. And you don't even have to spray yourself. You spray at the fan and you're standing in front of that motherfucker, it's just right back at you. It's why you don't spit into the wind. You know, it just comes back at you. But water under that air just fucking dries out quickly. But oh my God, water takes heat fast. Water is a great heat conductor. So if you're hot, it just fucking chills your skin super fast. I don't know why they use fucking ice when they need to do that. Like if someone's having a heat stroke, put that motherfucker in front of a fan and spray that motherfucker. The ice slowly takes it away, but that shit seems that because the ice is sitting there, like when you have ice on something hot, a barrier forms that the heat has to go through the water to melt the ice. But with the wind blowing over it, it's fucking sucking that heat away as it's doing it. They should do that. Yeah. Don't you use your fancy science words on me? I know it's evaporation. Get out. No.
It might be easier to transport ice though.
Then water?
No, a fan,
Oh, true.
right?
It's true. And fanning someone with like the big, but that's not the same. That's a lot of work.
But it's not nearly as good.
No, I had a student that took Calc with 3 with me a couple years ago. He's at San Jose State right now, I think. He comes back to Mesa every once in a while. I saw he came in 2 Saturdays ago. He's from China and he was back home with his family recently. I think either before the semester started or like mid-semester. Came in and brought me one of the good old like expanding Chinese fans. He had the best time laughing at me trying to open that motherfucker. I started to etch into it, like scratch like a little arrow into the side, like rotate this way. He's like, dude, it's the same either side. Flip it over, he's doing it. I'm like, oh, just go to the okay. He had to make fun of me for me to actually grasp what was going on. Because I kept trying to do it the other way. He's like, you're gonna break that shit. Stop. Just stop. Do this. And so I watched him do it and I started to scratch an arrow into it. He had a good time laughing at me. You guys ready? Anybody miss it? Did I pause the video? No, I didn't. We recorded all of Mikey Kinney's bullshit.
Perfect.
Brought to you live.
That's how it should be.
That's how it should be right there.
Don't worry, I gotta do some public speaking that was live streamed at Facebook, but thankfully the YouTube stream crashed, like way before I started speaking.
What's wrong? Why is that a good thing?
Oh, my speaking was terrible.
Did you get all nervous? You don't have a problem talking in here in front of everybody in class, including with complete nonsense like that 11D7 shit. Just do that. When you're public speaking, pretend like you're talking to Hefe.
There you go, I'll try that.
I'll tell you a fun story after this. Remind me to tell you about my first public speaking later on. We're gonna look at something called the geometric series now. And this starts with k equals 0 here, and it's a times r to the k power. So if I expand this out, this is a times r to the 0 plus a times r to the first power squared. And if you get rid of the exponents you don't need, like that. So a is the first term. And we use r because it has got to be a ratio. Or the factor that each term increases by. And there's a theorem that says a couple things. So that's the series. Here's the theorem that goes with it. This converges to a over 1 minus r if the absolute value of r is less than 1. And b diverges if r is greater than or equal to 1. What? Both of you get no. You're right. I was gonna do A and B. I have A and B in my notes, but I'm like, this is A. Why have two A's? That's fucking confusing. So like if you looked at it on a number line,
Is that absolute value of all?
yeah, that is absolute value of R. It's converging on this interval, but with open parentheses, not closed parentheses. It's looking like a fucking TIE fighter. Get your Star Wars reference in there while you can. So I'm gonna start off with we'll do the proof. There's a couple cases here. A lot of people start with an odd case, weird case first. I think it's best to start with the main case. S sub n is gonna be A plus AR plus AR squared plus plus AR to the n minus one plus AR to the n. And we are going to write what R times S sub n looks like. If we multiply S sub n by R, this becomes AR, and I'm going to write it over here. So that one's like there, and then we got AR turns into AR squared, so it's like that. We've got an AR cubed for that one there. This one is turning into AR to the n, and this is turning into AR to the n plus one. We did this earlier by multiplying by 2. Well, now I'm multiplying by R. Because 2 was the common thing in the previous one, and R is the common thing here. And now I'm going to subtract. Looks like everything is getting subtracted. That subtracts that, that subtracts that. If I lined that up better, that would subtract that. What's not getting subtracted is this A here, doesn't cancel. And we're subtracting that term right there, that doesn't cancel, the R to the n plus one. Yeah, this is some stuff you'd be like, nope, I wouldn't have come up with this shit. This is some clever girl velociraptor status shit right here. Well, S sub n factors out. And I will factor out the A over here. Maybe I shouldn't. Maybe I should leave it in. I'm going to leave it in. We're going to divide by it. And we got A minus AR to the n plus 1 over 1 minus R. Now, clearly we can see this approach does not work for 1. So we're going to say this is R does not equal 1. For us to use this just has to be the case. And if we take the limit of both sides, we now have the limit as n goes to infinity of S sub n. I'm going to separate this into 2 fractions. Limit as n goes to infinity of A over 1 minus R. Minus the limit as n goes to infinity of AR to the n plus 1 over 1 minus R. Or maybe this is a little bit better. Let's write this as A over 1 minus R times R to the n plus 1. That's probably a better way to look at it. That way you keep in mind that this 1 minus R is just a coefficient. R is going to have some value here. Well, this one is got no n in it, right? So that's just a over 1 minus r. The next situation gets a little tricky. In fact, I can pull out the a over 1 minus r, so we can focus on the critical parts right here. R to the n plus 1. So we got to break this down into some scenarios. If r is greater than 1, then the limit as n goes to infinity of r to the n plus 1. Well, like if this is 1.1 going to infinity, this goes to infinity and diverges. If we have r is less than -1, then limit as n goes to infinity of r, or sorry, of infinity of r to the n plus 1, kind of looks like the same thing as limit as n goes to infinity. I can have -1 to the n plus 1 times the absolute value of r to the n plus 1. Does that kind of make sense? I factored out the -1 because the exponent is going to alternate signs. This is going to cause the signs to alternate. But this part is now positive, and absolute value of r here is greater than 1, and we're back in the same boat. This part diverges. So if r is less than -1 and r is greater than 1, that shit diverges. But if r is between those, this means that we have a fraction where the top is smaller than the bottom. I.e., the top over the bottom, or a fraction, numerator over denominator, is less than 1. But the top is less than bottom. As this gets bigger, the bottom's going to infinity a lot faster than the top is, and this part goes to 0. You know what? I'm going to say less than. Nope, I can't say less than or equal to a -1 because I don't want to use the absolute or r equals 1 case. What happens with r equals -1 and r equals +1? Actually, I should finish writing what that shit means. Since this goes to 0, S sub n just equals the a over 1 minus r. That's what we had from right here. And -1 less than r less than 1 is also written as absolute value of r is less than 1. Because we are looking up here, that's getting a little blurry. And we've just been working with this one right here. We already have that locked in. If this diverged as it did in sum, the whole thing is garbage. But this is converging to 0 for that region. What about r equals 1 or r equals -1? R equals negative, actually, we can do -1 here. I can do -1 there. Does that change anything? It's still gonna alternate. And the R equals -1 part here, absolute value R, since it's a sum, is gonna, well, let's look at that one in particular. Let's start with R equals 1, going back to S of n. It's gonna be A plus A plus A plus A plus A, or n times A. It'll be n a's. And if I do the limit as n goes to infinity on this one, this is the R equals 1 case. The limit as n goes to infinity of S of n is divergent. And finally, let's look at the R equals -1 case. And I'm gonna rewrite what we're looking at here. AR to the K. So S sub n, K to the 0, -1 to the 0 is +1. So it's just A. So this is like AR to the A to the negative, well, fuck it, I better write it. This is A minus A plus A minus A plus A minus A. And it keeps going. If we do the limit as S sub n goes to infinity, or limit as n goes to infinity of S sub n, it keeps going. Now, depending on how you combine these, option 1, if you combine them like this, these all go to 0. But the question is, like, do we end on something that went away? We have no guarantee that this doesn't end. So we can't say that it goes to 0. Because if we do one term, if we do even number of terms, it's 0. If we do an odd number of terms, it's A. So this series, if we write it as a sequence, is going 0, 0A, 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 0A. As this is the partial sum sequence, this is divergent because it's not closing in on a number. So the only ones that it was convergent for only converged for absolute value of R was less than 1. And we had K equals 0 to infinity of A times R to the K equaled A over 1 minus R. We covered all the different possible scenarios of R, and that's what we came up with. Some of them, it took a picture, like doing R equals -1 isn't so clear. But if you look at this partial of the sequence of partial sums, you'll see that it's alternating. We don't have increasing or decreasing. It's not monotonic. It's not converging to a value. We have nothing that says convergent here. Ready for an example? Someone pick a simple fraction. A little bit more than 1/2. Anything but 2 on the bottom. 3/4, let's do 3/4. So we'll do the sum from k equals 3 to infinity of 3/4 to the k. So like the first term is going to be 3/4 cubed. Plus, then we'll have 3/4 to the 4th. Plus 3/4 to the 5th. And so on. If I rewrite this as, let's see, 3/4 cubed is 27 over 64. 27 over 64 times 3/4 to the 0. This is 3/4 cubed. Plus 27 over 64 times 3/4. I've already used up 3 of this 4. I've got a 1 here. Plus 27 over 64 of 3/4 squared, which is 5 minus the 3. This is 4 minus 3. This is 3 minus 3. I could rewrite this where we start at k equals 0 and have 27 over 64 times 3/4 to the k. Does that work for you guys? Does that make sense? So is anyone not clear on that? Because I will rewrite it another way. Everyone's good? Okay. So now we've got like an AR to the K. And we're starting at the right value, K equals 0. So A equals 27 over 64. R is 3/4, which is less than 1. So S will be A over 1 minus R. 27 over 64 over 1 minus 3/4. I just did the subtraction on bottom. And we will multiply top and bottom by 4 over 1. And we will get S, which is the original thing we started with, must equal 4 cancels out with part of the 64. This was 4 cubed on bottom. It leaves 4 squared on bottom, 27 over 16. All right. Rather than coming up with my own number, I'm just gonna wing with what we got here. No, we'll change it up. Or 0.267 with the 39 is repeating. And we want to express as a fraction. So I can write this as 0.267 plus 0.00039 plus 0.000 two more zeros and another 39 plus 0.000. I did 3 zeros, 5 zeros, 7 zeros here, 39, and it keeps going. And so that's going to equal, this is like plus 0.0039 times 1 plus 0.00039 times 0.01 plus 0.00039 times 0.01 squared. And this 1 here, I could write as 0.01 to the 0 power. I can actually rewrite this as 0.267 plus the summation of k equals 0 to infinity of 0.00039 times 0.01 to the k. So this part as a fraction is 267 over 1,000. You just multiply by 1,000 over 1,000. This is going to be a over 1 minus r, where a is 0.00039 and r is 0.01. So this is plus 0.00039 over 0.99. We're getting there. We don't like decimals and fractions. This has got 5 zeros on top, so I'm going to multiply this, or 5 decimal places. I'm going to multiply this on top and bottom with something that has 5 zeros. And to get a common denominator, it looks like I need to multiply this one by 100. That way I have 5 zeros on bottom. Or, well, we're getting closer. We have 267 over 100,000. You know what? I'm not going to do the 100 over 100 yet. Let's skip that part for now. I think I might have done too many. Let's just take it slower. This will be 39 over. I just want to fuck up basic math right now. So 100,000 times 0.99 is 99,000. So I guess if I want a common denominator, I gotta multiply this by 99/99, not 100. $267 times 99 plus 39 over 99,000. Now, clearly this reduces because this is even, they're both even, but without reducing, we got it down to a fraction. We should simplify, but that's a waste of our time in this class. Ready for another one? Are we having fun yet? Aaron? You're smiling, but you weren't nodding. Did anyone need that up longer? I pulled it. I didn't ask. If you need it up longer, say something. I'll put it back. Okay. Let's do some bullshit one. Let's do k equals. You know what? We'll start at 0. Now let's start at 1. Start at 1. It's nice to see some that start at some other value. Let's do like 2 to the 5k times 3 to the 2 minus k. So this is like having, let's see. Let's just look at the 2 to the 5k and 3 to the 2 minus k without looking at what's going on there. This is 2 to the 5k times 3 squared over 3 to the k. And that is like 2 to the 5th power, 2 to the 5th power times k times 9 over 3 to the k. So this is like 9 times 2 to the 5th power is 2, 4, 8, 16, 32. 32 over 3 to the k. And now I'll put my summation back notation back in there. Now that we got our rewritten into a form that looks familiar. Well, if that's our R, that's greater than 1. And that means this geometric series will diverge. All right, we got one more thing. And maybe I'll do it on another page. This is a new topic. This is called the harmonic series. The summation of k equals 1 to infinity of 1 over k. And it's the overtones produced by a vibrating musical string. And we will show that S equals k equals 1 to infinity of 1 over k, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot dot dot. We will show this diverges. We're going to prove it. Now, if you want to see one of the most fucking confusing fucking proofs ever, look in the textbook. I know some other teachers teach it this way too. It's a confusing proof. But what we're going to do is let's assume it converges. Let's assume convergence. And find something that makes a false statement. Find something that makes this false. And therefore, the assumption is wrong. Let me get rid of that S right there. Since it diverges, it doesn't really have an S. Right? It doesn't have a sum, so it's not going to have an S. But if it converges, it does equal S. So S is going to equal 1 over 1 plus 1 over 2 plus 1 over 3 plus, and we're going to do a bunch of terms here. And I'm going to rearrange these to group up the odd denominators. So S equals 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 7 plus 1 over the other odds. Plus then the evens, 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1 over like 2n. I guess this is like 2n plus 1. So we're going to leave the tail half the same. And what happens if I change this to the odd denominators or the even denominators? What if I say 1/2 and 1/4 and 1/6 and 1/8 and stuff like that? If this part equals S, this line right here, is this portion greater or less than 1/1 plus 1/3 plus 1/5 plus 1/7 plus dot dot dot? Trying to compare it to the line above. Well, the 1 is greater than the 1/2. So 1 is greater than 1/2. 1/3 is like 0.66 and or not 1.66, 0.33. 1/4 is 0.25. So 1/3 is greater than 1/4. 1/5 is 0.2. 1/6 is 0.16. So 1/5 is greater than 1/6. It turns out each one of these here is smaller than the one above it. So if this is S, S is greater than this. Because these values are less than. It's a smaller value. And so that's smaller than S. But now I've got two sequences that are the same, or two series that are the same. So I'm going to say S is greater than 2 times that, because we're adding them. Believe it or not, this is the less convoluted approach. As long as you can see that this sentence is true, this statement is true. You guys with me? Distribute the 2. All the bottoms are even, so we're basically dividing the bottom by 2. But what does that equal? It's S, right? So we're saying that S is greater than S. That's false. Which means our assumption must not be true. Because everything we did here was valid. And the assumptions was convergent, which means the sum of k equals 1 to infinity of 1 over k diverges. This one can't start at 0 because then we would have a 1 over 0 here, and that shit breaks. So this is one that has to start at 1. You know, I want to have a little bit more, and I think I could squeeze it in that corner, but I don't want to squeeze it in that corner. Let's just do a quick example, something for you guys to think about. Let's say we're looking at k equals 4 to infinity of 1 over k minus 3. So this looks close to the harmonic series. If the harmonic series is more like 1 over n. So like, let's say to match these up, I say n equals k minus 3. That would make this comparable, right? If n equals k minus 3, then 1 over k minus 3 equals 1 over n. And if k equals 4, because now we're going to want to rebrand this as n equals something to infinity. If k equals 4, then n equals 4 minus 3, which equals 1. This gives us n equals 1 is our new start. So I can rebrand k equals 4 to infinity of 1 over k minus 3 as something with a different index, n, starting at 1 to infinity and just going 1 to n. This is something where we can see this is harmonic and thus diverges. But this is a useful strategy, as you'll see over the next few sections. Sometimes I called this rebranding because I don't remember, they must have a name for it. But like in today's world, rebranding, oh, we're putting it under another brand. We're not using K, we're using N. Make it look like what you want to, or look like something you know. Using math, like what I did here, n equals k minus 3. Then use that to find where the new index starts. Using substitution of the old index. Of the old starting index. Any questions? That's all I got for you. You're free to go. You can get the fuck out. You can ask questions. I'll stick around.
So weren't you going to tell us about the story about when you was big parties?
Oh, yeah.
Oh yeah. So I attended Los Angeles Job Corps when I was around your guys' age to get a certificate in accounting, not a degree, just a certificate. And it's like a federally funded program that pays for your college or training program. A lot of people don't go to a college thing, but since mine was accounting, it was at a college. And I had top grades and one other person had top grades. And we had to like submit, they wanted one of us to be the speaker at like the graduation. And I was like, you know what? I think I could do it. We had to submit what we would say in our speech and they picked the better speech. There was me and another guy named Richard Whiteside. He was just as good. I was named public speaker. He was given something else. And when they called me up to speak, I knew the order. I knew I was next. And the lady introduced me as David Whiteside. I heard David, I started to stand, I heard Whiteside, and I fucking faltered and like stopped like partially out of my seat. Richard's sitting next to me. I was like, no, she fucked up. He gave me a little shove and pushed me up there. I was like fucking completely off my game. I get up there and there is like fucking, it's a giant auditorium. There's gotta be 1,000 people in this fucking room. And I see one of my friends, this was in Los Angeles, my family and a couple friends drove down from Sacramento, which is where I was living. And one of them stood in the back and yelled, "Go Pump Dave!" They used to call me Pump Dave. I don't know why. There's a couple Dave, the guy that said it was Dave also. And I looked up and I saw him and I smiled and I just looked like, I looked at him and then I would glance, as I looked around the room and got uncomfortable while I was speaking, I glanced back to him and he's like, fucking doing a dance in the back of the room. Like just trying to keep my attention so that I wouldn't fuck up my speech. And I got through it apparently pretty well. I was told it was all right. But there was a lot of fucking people and I was just supposed to fucking panicking. I did take a speech class in college. It was like a communications class, but on public speaking. But it's only in a classroom, so you only practice giving short speeches in front of like a class size of 30. It did not fucking compare.
Yeah. Mine was all right, but like my hands were shaking so bad through the whole thing. But I was standing behind a podium, so you really couldn't see it for the most part.
So was I, but like you see here, the top half, but. Yeah,
So,
but since then, everything has been easier since that first real public event. Because like. I guess it kind of.
yeah, no, that was the first.
Let me
one.
like
Got it.
pause, stop this video before it gets recorded.